So I'm sharing my slides. Can
Yes,
you see?
yes, I can see. Thank you.
So I'll start my presentation. So I introduce paper written by Fuyama-san, Saigo-san, and Takahashi-san. The title is A Category Theoretic Approach to Metaphor Comprehension, Theory of Indeterminate Natural Transformation, written in 2020, appeared in Biosystems. So please let me explain why I chose this paper. So my research theme in the Korea structure is a structure of neural networks related to color Korea in dreams. So far, we have collected more than 500 dream reports and relevant neural activity data. Here is an example dream report. The image of oneself continuously climbing upward, building a wooden brown staircase made only of threads and risers, reaching towards the blue sky with white clouds. So this kind of dream image is created in human mind without any external stimuli. So I think dreams may be created through indeterminate process of associating images. So I wonder a category theoretic approach with an indeterminate nature may be useful for the analysis of dream reports. So in introduction part, they stated that our minds are filled with various images, like the images of a cup, snow, red, cold, goat, number 3, etc. And these images can be in any modality, whether concrete or abstract, verbal or non-verbal. Each image appears in our minds with rich meanings. Several meanings are being created in our minds. Meaning creation is fascinating cognitive process in humans. So aim of the research is first investigating the process of creating meanings by focusing on novel metaphors as an example, and formulating the process of novel metaphor creation in terms of category theory, and proposing a new theory of novel metaphor comprehension, the theory of indeterminate natural transformation, TINT. So under this theory, the meaning of a certain image is defined as the entire associative relationship of the image to other image. So here is an example of the meaning of love. The love is associated with other images. And when a new metaphor, love is like water, is introduced or evoked, so this changes and enrich the meaning of love. See? So in the last figure, after formulating metaphor comprehension by using terminology of category theory, they show the example of how we can interpret poem, the metaphor hidden in the poem by using this diagram. The title of the poem is Soil. An ant flew a wing of a butterfly, or it is like yachting. So they thought novel metaphor comprehension is a process of constructing new local or partial correspondence between a part of this associative structure between two images, source and target. So these are word or images appeared or are maybe metaphorically represented in this poem. And I marked the word appeared in the poem with green circle. And as you can see on the left side, many words, there are many words appeared in the poem. So I think, so they define this is a source source space or kind of source part, and the target is images that is metaphorically or created by a metaphor comprehension. So, and I think we can say the source is observable images and the target is expanded meaning or created by metaphor. This is a last can I say explanation in their paper. But before going to formulate the metaphor comprehension by a category theory, they introduce basics of category theory. So maybe I can skip this part, but more I'll briefly introduce. So a category is a system composed of two types of entities called object and morphism, which relate through the notion of domain, start point, and codomain, end point, which is equipped with composition or composition of two morphisms and identities that indicates for any object X, there exists a morphism called identity. And so and this relationship satisfies associative law. So for the diagram on the right, it is assumed the composition of H and G after F is equal to H after composition of G and F. So composition of this and this is equal to this and this. So when all morphism compositions are equal, the diagram is called commutative. And maybe so next from then they introduce the definition of natural transformation. So and the functor is a structure preserving correspondence of two categories. Let F and G be functors from category C to category D. A correspondence T is called a natural transformation from F to G if it satisfies the following condition. The first condition is T maps each object X in category C to the corresponding morphism in D. And second condition is for any morphism F from X to Y in C, composition of T1 and F1, Ty after FF is equal to GF and composition of GF after TX. So this indicates they are commutative. So here is an example of a discrete or with discrete category with discrete number. So TX if object of X is like a discrete number, so in category C, corresponding morphism can be made by this natural transformation in category D. So in figure 1, the authors formulate the metaphor comprehension by breaking down a category into costless category A under C and costless category B under C. The costless category A under C indicates object A in category C is many relation with images Y out of Y, and in costless category, objects of category theory, objects of costless category is morphism from A to any Y. And morphism of costless category is this triangle relationship. So maybe the similar likewise in costless category B. And now they assume when a new metaphor expression A is like B is introduced or evoked. The base of metaphor functor F under C is canonically created by these morphisms using composition. And more natural interpretation of the metaphor is made as another functor F by natural transformation from F after C. So the authors hypothesize that construction of meaning is morphism from base of metaphor functor to a new functor. So this morphism is this morphism is natural transformation. This. Then the further models indeterminate nature of meaning creation by introducing stochastic category. So briefly, so this is composed of a probabilistic weight on morphism and excitation and relaxation rule. And these rules are applied depending on the compositionality. And especially for fork rule, this kind of compositionality of morphism is needed while searching for natural transformation. And so the left figure 3 illustrates how stochastic weight works in their model. And each morphism has stochastic weight mu. And when mu weight is large in the part of stochastic category is excited, and that is excited category metaphor. And I think this is related to consciousness. And they describe that dynamic process of metaphor comprehension is modeled as an alternation of categories and functors from moment to moment. So this describes that metaphor comprehension is fluctual, maybe. Depending on the situation. And the interesting part for me was weights weights change by continuous excitation of this maybe structure and feedback, connection, or learning, etc. And altering our worldview. This is an interesting point for me. So in summary, TINT enables an efficient search of an analogical mapping than previous algorithms because it starts with a trivial mapping based of metaphor functor and shifts gradually to a more meaningful mapping through the construction of a natural transformation. So here is the things that were difficult to understand for me. So in figure 1, then when they formulate metaphor comprehension by category theory, they said that based on metaphor functor F under C is canonically created by these morphisms using composition. And I couldn't understand well why what is canonically created means. Maybe it's related to this relationship. And if so, how are compositions in this diagram relate to the commutative diagram here? This is my first things I couldn't understand. And next one is in figure 6, explanation of figure 6 is author said that a morphism cell to soil will be searched under some indirect path B2 after F that is equal to TB2 after B2 with a transient point C. And the hidden image C is excited and morphism TB2 becomes a part of the indeterminate natural transformation. I think this notion is very interesting point. So the hidden image C is excited. Very interesting. But I couldn't understand what is the source structure or morphism that creates the natural transformation with TB2. And I wonder, isn't B2F morphism from wing to C in this diagram? But I'm not sure. So these are difficult things of the paper, me. And the things that I want to discuss in the grand meeting is as follows. So that is whether it's whether category theoretic approach is useful for the analysis of dream levels. So this is a dream I introduced in the first part, and second dream example is like this. I carried navy blue, light blue, and white clothes and put them in the washing machine. So this is an example of dream, and so I want specific point is what I want to discuss is it possible to establish a relationships between dreams or analyze their structures by using category theoretic approach, and how can we relate dream structure to neural data or structure? That is further point I would like to discuss in the grand meeting. So I tentatively mapped this dream by using images that appeared in each dream, but I'm not sure this mapping is okay. So any comments are appreciated. That's it. Thank you very much for listening.
Okay, thank you very much. Let's open the floor now for questions and discussions. Okay, Francesco, would you like to turn on your mic? And
yeah, no, I was actually just reacting to the talk, but yeah, I must say, actually, I had the exact same question of canonically created. That I don't understand it. Well, I just don't understand.
okay, let me respond then. The canonical, usually canonical means some sort of universal, some sort of special universal construction. And a typical case here is what's called the pullback.
I see. Mm-hmm.
And so when you, at least in sheaf theory, when you have a function, what's called a continuous function between two topological spaces, that induces a pullback of the from one space to the other in the same sort of reverse direction as indicated there. Although in this paper they're using co-slices, which is not exactly the same. The situation is quite analogous. And so the notion is it's not just any map, but it's a particular map that satisfies a universal property.
Mm-hmm.
But usually canonical is meant in two senses, either just as a synonym for universal mapping property or a particular universal mapping property. For example, when you talk about the product of two sets, you say it's canonically the Cartesian product. But there are other products of two sets that are also equivalently products, but not. It's called a canonical in that sense because conventionally, when we take it as element from A paired with the element from B, but you can also reverse the pairs, and that's also a product, but it's not called a canonical product. But in this is, I guess, is what they mean here. That is that the the functor that's induced is the one that satisfies the universal mapping property. And in the sense that Francesca mentioned in the previous talk, it's kind of a best one.
Sorry, this
It's a kind of best, it's a, in a categorical sense, it's the best way to do it.
way to.
Yeah, kind of
Sure.
optimal.
Oh, I see. Thank you very much for your explanation.
Thank you, sir.
Okay, any further questions?
I have a question.
Yep.
So some metaphors are simple and some metaphor can be complex, some like those that we can find in poems. And I want to know if the category, the tint model imply any hierarchy between metaphors or between basic meaning or basic metaphor to complex metaphors.
Okay, thank you very much for your question. I think the authors considers that part, and so authors argue that this this relationship, ring is like cell, is the most salient metaphor in the poem. But according to the so depending on individual, the most salient metaphor might be different. May differ between individuals. So if so, the hierarchy might be different between individuals, but there should be some hierarchy or simple or easily metaphor easily found, that is easily found, and metaphor that is difficult to found, and like relationship by like soil, relationship between soil and sea. So soil and sea can be searched from by using other relationships. So I think this is a complicated or higher metaphor hidden in the poem. So I think the authors already considers a hierarchy or complexity of the metaphor, I think.
Thank you very much.
Maybe Kusano-san do it.
Yes, thank you for your presentation. And I'd like to ask you about how do you see this TINT model being used in your dream research?
How I view this approach.
I would like to ask you about your ideas.
Thank you very much for the question. So because I am a very beginner and so beginner is of a category about category theory. So my understanding of category theory is very shallow. So I intuitively thought this might be applicable to, how can I say, maybe analyze or relate between dreams. So if and possibly by incorporating topology or numerical, if category theory can expand to treat numerical data, maybe we can relate these dream report with neural data somehow. So if any of you have some ideas, I'm very grateful.
So to answer your second question and that question then, a general point to realize here is that there may be many possible natural transformation, maybe several natural transformations between two functors, and so you may need a sense in which to order them, what transformation is particularly salient compared to other transformations. And in this particular model, it's the strength of the associations, I think, that sort of implicitly order the indeterminate natural transformations. So that's one thing, and it should, and because you're comparing structures, the optimal transport approach for comparing structures is another approach, but actually optimal transport is a special case of a particular type of category 3 construction. So there is a connection that way. For example, if you're just dealing with the point of this paper here, using the stochastic thing, is to place some sort of numerical measure on the arrows to give some sort of strength of associative connection, and it's those strengths that sort of determine which are the preferable mappings. So in the case of your dreams example, is there some way to measure the strength of association between the images and so forth? That would be one consideration.
Thank you very much for your suggestions. So regarding the strength of connections, maybe I cannot say that any connection, which connection is stronger from one dream. But if we, how can I say, we analyze 4 dream data, maybe my hypothesis is there is some strong connection in humankind. So, for example, there is some observation regarding color from many data. So usually natural object materials like wood or natural object sky or materials tend to have specific or inherent given colors, like brown, sky is blue, wood is brown. But artificial objects here is clothes can be associated with any color. So, so these artificial objects tend to have various associations. So, but the natural object have strong connection to certain color. So I think these are some maybe things, of course, but maybe we can how can I say it, determine strength by using the current data.
In that case, yeah, something like optimal transport, which tries to is a kind of a measure of moving from one dream to the other dream. Maybe one way to think about this. The general difference here in the ordinary category theory, where the arrows are just where the relations between the objects are just sets of arrows, is how to compare sets. There's only really one way to compare sets, and that's by their cardinality. So, but with sort of that's a very weak, a very coarse way of doing comparison. So you want to enrich the relations between objects by adding additional data into the so-called Hom sets, or the relations between the objects. When you do that, that's called an enriched category theory, and it allows you for other possibilities. The most basic ones, for example, you can impose an order on the set of relations between objects, in which case you have a partially ordered set, and then you can do a comparison between partially ordered sets. Now, the one that that motivates most of the empirical work in the current project and the quality structure project is to consider just the relations as distances, and this is enriching. This is called enriching the category in terms of a metric space, as a metric space. And then the way that connects to optimal transport theory is that how do you move from the distances in dream A to the distances in dream B in some sort of optimal or some sort of, and because you're using the term optimal here, you can already suppose that it's some kind of universal construction. The universal construction now is in the context of numerical values and distances and so forth. That would be one way of doing it. Mm.
Thank you very much for very thoughtful suggestion, but I'm not sure my current knowledge of category theory can by using current knowledge is enough to do such analysis. But I hope I can deepen my knowledge a bit.
Yeah, so there's really 2 points here. One is, or 2 questions here. If you just want to do some sort of numerical comparison, then there are many techniques that are available without having to worry about category theory. And however, category theory itself may suggest some techniques that are not currently immediately obvious. The problem is how to link the category theory with those techniques, and that itself is not necessarily straightforward. However, as mentioned before, the optimal transport approach, which is prevalent in our project, would be one way of doing that, since that sort of connection has already been made. It is quite challenging actually to go from the category theory to something numerical like that without a lot of experience in both the numerical techniques that are already available and the relationship to category theory. However, some people have already done that in the case of optimal transport theory. It's really just a question of whether or not the extra formalism in the form of category theory is going to give you something additional. I suspect it will, but it's not immediately obvious in what way. So, I mean, just to get off the ground, you could just start with some of the ordinary techniques. For example, things like graphs and graphical models are already very close to some sort of category theory construction. But those sorts of models themselves may be sufficient for your task. If so, then you may not need the extra category theory. But, however, they may not be sufficient. They may have some sort of limitations in some way in that case. Yeah, the extra category theory may help. So while I would not dissuade you from learning category theory, there is a lot to take on there. And maybe some of the existing, you bootstrap your way forward with some of the existing numerical methods first. Yeah. Nonetheless, yeah. The point of the paper, though, is that the general point about any sort of graph matching is it's quite a hard problem, computationally complex, and so you need some sort of constraints on the problem, some sort of assumptions. In their particular paper, the assumption that the original metaphor is gives you a sort of a starting point from which to look at the possible maps. So it constrains the kinds of maps. This is kind of familiar in cognitive science in the form of the theory of analogical reasoning and so forth. It was already well recognized that just simply doing some sort of graph isomorphism as a solution is not going to work for large source and target situations. And so what they typically do in analogical reasoning have some introduce some sort of a bias, for example, some sort of semantic features that sort of encourage certain kinds of objects in the source to match with certain kinds of objects in the target, to cut down the computational complexity of finding a suitable analog.
Oh, thank you.
And that's essentially the role of the F in this situation here. And that's the reason for doing the co-slice category. So the object on which the sort of root object here is kind of grounding or constraining the possible matches that you can do. So, that's
I think in regard to dream reports, I think self might be kind of I don't know, the constraints or in my research, maybe color and relationship between color and object and all.
Yes.
And so, but these are composed of different image or different modality, or how can I say it? Different level of images. For example, self is about self and others, and this is object to be image. So, so maybe there is some constraints in dream levels. So if we set some constraints on dream levels, maybe the analysis might be possible. I think.
Yes. So in the spirit of the co-slice approach, if you can analyze dream A for some object or something that's sort of fundamental or what we call initial to all the other objects. So the general feature of the co-slice category is that object A that's under which or over which all the other objects sits is kind of initial to all the objects. So all other objects point to it. So it's sort of like a ground point. So if there's some way in which you can analyze the parts of dream A for that sort of initial object and do the same for dream B, and then use the link from link between those two initial objects as sort of your starting point, that would cut down the complexity of the matching problem. And that's a little bit different from optimal transport theory, because optimal transport theory doesn't assume any particular special object within the domain, the domain or source and target. So in that sense, yeah, the co-slice approach has some potentially interesting novel approaches towards the way you do the numerical analysis. But like you said, maybe self, some concept of self is sort of core to dreams. Gives it the immediacy of the dream, I suppose. And so if there's some way of analyzing that within each dream, and you can use that as the basis for the transformation, that would be potentially fruitful.
Thank you so much. Yeah, I saw I of it, and so so all of your suggestions encourage me.
Great. Excellent. Okay. Any further comments or questions? We are now 10 minutes over, but feel free to continue. Yes?
I have a question. Oh,
I'm sorry, I missed that question.
no, I'm asking, is there anybody who asked first? I cannot see. Oh, because I want to ask a question. I have a comment.
Yep, go ahead.
So you suggested to use graph theory to map different meanings, or like for her research about dream. I think graph theory compared to category theory is more rigid. I think it's unidirectional. I think the vector between the what to call it, the object, for example, that has to be connected to each other, is just like unidirectional, and it's not possible to make a sort of loop and come back to the same object that was previously associated. And the point of using category theory for dream research, for her dream research, could be, I think, useful, since it's neuroscientific, a neural study, and there are constantly neural connections that are activated. And they said that using tint, the tint methodology is very flexible and can be adapted to instantaneous data, or instantaneous data coming constantly to whatever. They need to have like something that is dynamic and instantaneous. And I think category theory can be a good match for her research. But for graph theory is not something that they can use, that she could use for research, since it's quite rigid and less flexible than category theory. I'm not sure. Like, what do you think?
Okay. Yeah, the relationship between category and theory and graph theory is an interesting one. It actually goes the other way. So graph theory is less rigid. The reason for that, and hence one reason why you want to use category theory, is that it poses some additional constraints that directed graphs in general don't have. One of those constraints, as mentioned in the paper, is the compositionality constraint. So, for example, if you take the arrow from sky to clouds and clouds to white as a graph, you don't need to have as a category, you also need an arrow from sky to white. That's the composition of the two arrows. So 2 arrows end to end must have, if you have 2 arrows end to end, you must have a third arrow that combines the two. And that's that additional constraint that provides the extra structure of a category imposed on the dream A. And if you have extra constraints, then you can potentially cut down the computational complexity or the alignment. Now, directed graphs in general don't have that, although you can impose them onto the directed graph. There are slightly other reasons as well, but your general point is reasonable. It's just that it goes the other way. In general, the graphs are less rigid than categories, and it's for that reason you get these things like the unilateral, because there are additional constraints for being a category on top of being a graph, that you have things like the unilateral lemma that you don't have in graph theory, which allows you to do certain kinds of inferences that you couldn't do without it. So the general point there is the reason for taking a category theory approach is that it may encode there may be some additional structure inside the dream that is encoded by the category theory approach. And since the functors to be a functor, you must preserve that additional structure. It cuts down the possible ways of aligning it. Now, the crucial question, of course, the crucial empirical question, of course, is whether that aligns with what you see in people. Okay, and so if it does, then that's great. And it's one reason for using category theory and not graph theory. If it doesn't, that's the way it goes. Yeah, and a very good question.
Thank you very much for your explanation and your clarification.
Okay. Francesco, any comments or further questions? Since we've spent more time on Chiro-san's, would you like to go back to something that you wanted to ask?
Maybe Kusano-san, do you have a question?
If we have a spare time, I have a small question.
Yep, sure.
Okay. You said I was curious about the optimal transportation theory being a special case of transport in category theory, because as you said earlier, it doesn't assume any special object in the transport.
There's a slightly nuanced way of saying that. The optimal transport theory can be regarded as a special kind of category theory construction, but not specifically co-slice construction. The word there, the key word there is profunctor. It's a bit technical to talk about, but the basic idea is that this was pointed out by someone quite a few years ago, a category theorist. That the way that you do optimal transport by sort of a mapping between mappings is analogous, or can be considered as a mapping between profunctors. Now, the profunctor is all about a generalization of the notion of a functor, a bit like the way that a relation is a generalization of a function. So it gives you more flexibility, and the kind of flexibility that you get. And the reason why I say the other point, the reason why I was going back to the previous point, is that the co-slice category, by its definition, fixes a particular object in the category that you're talking about as the initial object. Now, in optimal transport theory, you don't make such assumptions, and so it's a different kind of relationship and a different kind of category theory that's used there.
I see. Thank you for clarification.
Very good. But having said that, you could, in principle, I suppose, you could sort of have a variation on optimal transport theory. Apparently there are many variations in optimal transport theory that people have tried, and in principle, you could do something analogous by supposing that there is each domain, each source and target has a special object, and then do your optimal transport with that assumption already embedded in the way that you do the thing. I don't know how you do that, but you know, in principle, it should be possible, I guess. It's a bit like when you any kind of optimization, you can just add additional constraints, you know, so-called regulation. I forget what the exact term is, but on top of your optimization function that sort of favors some sorts of solutions over others. Yeah. In principle, I suppose you could do that for optimal transport theory as well, and for this dreams problem. Because one of the problems with optimal transport, because it's kind of a, because you're comparing, it's kind of a, it's not a power, I think, but it's it gets pretty expensive for large graphs to do comparisons, because you're not just comparing objects with objects or nodes with nodes. You're comparing edges with edges and all possible edges with all possible edges. So there's a kind of an explosion in combinatorics there. Now, if you were to fix some of those nodes as, yes, saying that these two must align, then that will dramatically cut down the combinations that you have to consider. You know, so maybe that's worth considering, sort of merging or blending the sort of co-slice approach with the optimal transport approach in some way, which may help. Now, of course, you have to have a motivation for doing that, and maybe in the dreams, since dreams are first person, you may assume that there is some node that corresponds to, you know, your intrinsic self, i.e., the initial node, which relates to all other, you know, associations that you have in your mind at some time. And likewise, assuming that the intrinsic self doesn't change, then you can make the same assumption for the second dream, and that would help really constrain the kind of alignment that you'd like, optimal alignment that you'd like to find. Okay. I hope that was didn't muddy the waters.
You were talking about merging, so I was thinking that maybe, for example, you collecting witness with a story from someone, and the story has different events, but probably the more you're telling the story, there is a loss of some information happening. And I'm not sure if applying the merging methodology from the merging angle of your idea regarding the category theory in this kind of context where there is a loss of information or some information are merged together. Do you think it would be relevant in this kind of context?
Yeah, I'm not sure, but if there, from a purely formal perspective, if you have a loss of information, that means the map from the source, the domain, into the codomain, will be not injective in some sense, which means that more than one object in the domain will map to the same object in the codomain.
Yes.
And that would, in that sense, so once you get to the codomain, that object, you don't know which object you started from. So in that sense, you have a loss of information. Now, I suppose you could impose a constraint on your optimization to encourage maps that are not injective, and in that way simulate some sort of loss of information. That's a guess, but that's all I can think of at the moment. Yeah.
Thank you very much.
Okay, do we have any more comments or questions for one last round? And if not, let's call it a day and meet again in the near future. Okay, thank you, Francesco, and thank you, Chihiro, for very nice presentations. And thank you, Kusuno-san and Misa, for attending and your comments and discussion. See you soon, I guess.
Yeah, see you soon.
Okay.
And
bye.
Thank you so much, Stephen, for being the MC for this session. And thank you everyone for the participation.
Yeah, no problem. Thank you.
Yeah,
See you
bye.
soon.
Thank you very
Bye.
much.